All right, today we're diving into a data structure that honestly kind of breaks the rules. It's not always balanced, a single operation can actually be pretty slow, but it's still one of the most efficient structures out there for certain real-world problems. We're talking about the adaptive magic of splay trees.
So let's kick things off with a question for you. What if the data you stored could, I don't know, anticipate what you need? What if it could just reorganize itself automatically so the things you use the most are always right there, right at your fingertips?
You guessed it, that's pretty much the core idea behind splay trees. They are this fascinating type of self-adjusting binary search tree. And the concept is really simple, but super powerful. Whenever you access an item, the tree literally reshuffles itself to move that exact item all the way to the top, right to the root. Okay, so how does this whole self-organizing thing actually work? Before we get into the nitty-gritty mechanics, let's start with a simple analogy, just to build up our intuition. I want you to imagine a magic bookshelf. Every time you pull a book off the shelf to read it, it doesn't just go back where you found it. Instead, poof, it magically slides to the very front of the shelf. So the next time you need that same book, it's right there, no searching required. That is the beautiful, simple idea behind how a splay tree operates.
So that's the what, but what about the how? How does this magic bookshelf actually do its thing? Well, it all comes down to this process called splaying. This is the engine of the tree, and it's built on three fundamental rotational moves: the zig, the zig-zig, and the zigzag. Let's break them down.
All right, first up, we've got the zig. This is our simplest move by far. If the item we just grabbed is a direct child of the root, all we do is perform one single rotation. And that's it. The child becomes the new root. Super simple, super effective.
Next is the zig-zig. This one handles cases where the node, its parent, and its grandparent all form a straight line, like three left children all in a row. Instead of one big move, we do two smaller rotations in the exact same direction. The parent rotates up, then our node rotates up, moving it two whole levels closer to the root in one single operation.
And rounding out our trio is the zigzag. This is for when the path is crooked. It's like there's a kink in the path, right? Where our node is a right child of a left child or vice versa. To straighten it out, we perform two rotations, but in opposite directions. This move cleverly brings the node up two levels. And believe it or not, these three simple rotations are the building blocks for every single splay operation. Okay, I know what you're thinking. That sounds like a lot of rotating and shuffling around. And it is, but it all builds towards the most important and frankly, the most misunderstood feature of a splay tree, its performance guarantee. And the answer is probably not what you think.
See, splay trees play the long game. They don't promise that every single operation is going to be lightning fast. Instead, they offer something called amortized time complexity. The best way to think about it is like a monthly budget. You might spend way too much on one day, but over the course of the whole month, your average daily spending is actually pretty low. Splay trees promise that same kind of good average performance, but over a long sequence of operations.
It's kind of the tortoise and the hare of data structures, if you think about it. A single, really unlucky operation, our tortoise, could be painfully slow, taking linear time, or O of n. But here's the catch. That slow operation does all the heavy lifting of reorganizing the tree. It makes future operations way, way faster. That's our hare. So over a whole sequence of operations, the average cost becomes an amazing, you guessed it, O of log n.
And this is where we have to bust a really common myth. A lot of people hear self-adjusting and think splay trees are always balanced, like an AVL tree or a red-black tree. That's just not true. A splay tree can actually become really lopsided for a moment. The real genius here isn't about maintaining a perfect, rigid structure. It's about being incredibly adaptive to how you're actually using it. Okay, so given this kind of weird performance profile, right, where you have this amazing average but a potentially bad single operation, where do you actually use a splay tree? When is it the right tool for the job? Let's really put this into perspective. You've got AVL trees, which are super strict about height balancing for that guaranteed fast lookup. Then you have red-black trees, which are a little more flexible, making them a fantastic all-arounder. And then you have splay trees. They're the specialists. They don't even need extra memory for things like colors or balance factors. They're making a bet. They're betting on one big thing, that the way you access your data isn't completely random.
And that bet pays off big time in the perfect scenario for a splay tree, which is when you expect what's called temporal locality. It's a fancy term for a really simple idea. If you use something now, you're probably going to use it again soon. Just think about it, the last file you open on your computer or the last variable you used in your code. Chances are you're going to need it again pretty soon, right? That's why they're absolutely perfect for things like CPU caches or compiler symbol tables. When that kind of pattern exists, a splay tree is an amazing choice.
All right, so let's bring it all home. As we wrap this up, what are the key things you absolutely need to remember from all this? What should go into your mental toolkit?
If you walk away with anything, make it these 3 points. 1. Splay trees are self-adjusting. Whatever you touch, they bring it to the top. 2. Their performance guarantee is amortized O of log n. It's all about the average, not the single worst case. And 3. They absolutely shine when your access patterns aren't random, when some items are just hotter than others.
And that really leaves us with one final, bigger question to chew on. Splay trees show us just how powerful adaptive systems can be. They don't force a rigid structure on the world. They evolve based on how they're used. So the question is, if our data structures can be this smart and adaptive, what other parts of our technology and software should be too?